implementation. However, recruiting actually probably is a better implementation. And one of the things I found on Friday, when I was doing the labs with the people that were there, I want to show you that sometimes you really have to do recruiting because sometimes you can't function without it. So one of the things I like to do in my lab sessions, yeah, it's on this website, if you want to channel. So in our lab, what we're doing is we go to Project Euler and we try to solve each one of these problems. So the first one is actually pretty easy, multiples of 3 and 5. So you usually go to the actual problem and then you try to find the solution. And then you can create a free account, you can register, and then you can get into the calendar to do a self-assessment. So here, the challenge is, the problem is this, listing all of the values that are multiples of 3 and 5, and then doing the sum of them. So if we do the all list all the acronyms below 10, then multiples of 3 or 5 will get 3, 5, 8, and 9. So then you add them together and the sum of that is 23. But then the problem is you do the same thing but with the values below 1,000. And our first one is actually not for this one, I just wanted to, so the solution here is just have our max value of 1,000, we have a counter, where we give each value, and if the data counter that value is modulus 3 over 0 or modulus 5 over 0, then we're going to add that to our sum. And so we ended up with the value of 233, 168. And the answer is correct, so submitted it. So the next one here, though, the next problem. So Fibonacci is a very traditional problem to solve with recursion. Because what you do is you come in and you add the previous value to your current value. So with Fibonacci, what you end up doing is, so you, by starting with a 1 and a 2, you get the first 10 terms. So how do you take that 1 and you add it to 2 and you get a 3? And then you add the 2 and 3, 55, you add 3 and 5, 58, and 5 is 13, 8 and 13 is 21, 13 and 21 is 34, 21 and 34 is 55. And you can see how that's Fibonacci. That's a very traditional recursion problem. And so here, it says now to see value is 1 million. So we're doing this in lab, and we're able to get up to 3 million, doing it in an additional 4 loops. Okay? So up to 3 million, the value of the sum of just our each numbers is 7,316,672. But we're just doing it in traditional form. So look what happens when we try to do 4 million. Look what value we got back. There's no way that's right, right? It's not any negative number. So we got to the point where we kind of like, you know what, this isn't going to work without recursion. So this is an example where it does not work without recursion because it's just too big. It's too thin, and it's not precisely that way. So I need to re-implement this in recursion. Anyway, so here we can do an iterative solution, but sometimes it doesn't work out, and so recursion will help us with that. And so recursion is just a function that calls itself. And so in this case, we had our example here was there was a sum of squares, and we had a value of m and our n. And if we were not in our base case, the base case is how do you going to stop our recursion. And so when you have a base case, this gives you the solution directly versus doing a recursive call. So this is given a solution directly versus doing a recursive call like this. So what recursion does for us is it breaks it down to smaller problems, subproblems, by making it manageable. And this is very indicative of agile methodology in software development, where you're getting a really huge project around, oh man, this is exactly something that you would release an 8-hour or less task. You have to be really careful with recursion, but if you don't ever meet the condition at the base case, you're never going to get on it. So you need an infinite loop. So one of the things we talked about is going up recursion. And going up recursion, we start at the low end of the increment up to the high end. So in this case, we're saying the m is 1, n is 10, and so we're trying to increment m up to 10, up to the value of 10. And so that is our going up recursion. And then we have the going down recursion, and we go the opposite way, where you decimate. Excuse me, where m is the value that you're trying to get to, and n is the one you're going to modify as for each iteration of your recursion. We also have the option to split it in half. So like, it'll find the middle value, the range. So in this case here, we have 11. So 11 divided by 2 is 5, because it's doing integer math, which is not the decimal, but going to portion. We split the range in half, and so it does the x piece 1 half, the recursion, and the x piece the other half of the recursion, and it adds anything. So we finally got around to the powers of noise, which is very important to understand. So it really is just a game or a puzzle. Very traditional recursion problems is like Fibonacci. So it has the 3 rods and some number of disks of different sizes. The puzzle starts where the disks are in ascending order of size on one rod, and then you have to move it to some other rod, either the second or the third one. So it's just kind of what it looks like. So what you want to do is move that entire stack to another route by obeying the simple rule. So only one disk can be moved at a time. Each move consists of taking the disk that's on top of it, on the other rod, and those disks can be placed on top of the smaller one. And so the mathematical equation that goes with this is what are the minimum number of moves to solve this puzzle. And the mathematical equation is 2 raised to n power, where n is the number of disks, and then it's times 1. So here I have some images associated with this, but honestly the best reference is the one that I posted on WebPerson. So this is the reference that you want to go to understand. This is the best visual reference I've seen. Okay, so the great thing about this reference here is that we literally trace the power solution step by step. And you can see how it functions. And you can also look at the callback down here, down below, the visual representation of how each one of these happens. And so no, it doesn't do it all the way up to the value of 5, but you can get a good feel for how it functions. And so what happens is it keeps from the top, it continues to break out each one of those proofs of function calls. follows the left leg all the way down to the first one. And then you see how the right leg is created with this function call here. And then it does all the function calls for the left leg. You can see how it looks through here. So this is one of those things that you definitely want to understand. And not just for the exam, because I think the foundation exam, you really do care about this because it's going to more than likely be on the exam. And so understanding this process is very helpful. So there's also this other example I showed you in class where it was showing you how the discs are moving, just the discs themselves. And that one has 4 discs. And so the minimum number of moves would have been 15 because 2 to the 4th power is 2 minus 1. So we decided that powers and Hanoi, well, I decided powers and Hanoi was way too hard to explain without stacks and cubes. So we talked about stacks and cubes. So what happens is, so with stacks, it's really just like putting a plate on top of one another, and you can't pull that bottom plate out. You have to take the plate off from the top. And so the terminology is you associate this when you put something on stacks, you put something off stacks, it's on the off. And you're always dealing with the last. So the last and first out is the approach. And I have my wonderful little example here on hesitate to discuss it because that methodology is very difficult to understand. So, but this is a push down stack. And so when you out to do it, you push down. And then you take something off of it and pop it off. They're pushing versus popping. They really are inverse operation of each other. So if you push an object onto the stack and you really pop it off, the stack is going to be unchanged. So if you look at this visual representation here, with the value of 5, if we push it onto the stack and then we immediately pop it off, the values of 1, 2, 3, 4 have not been modified yet. So why do you even care about stacks? That's how a lot of your computer program and your computer actually functions. Because they use the concept of stack implementation to actually do that for your assignment to create your list and the stack implementation of certain methodologies, so you're pushing it onto your source code. I found with stacks, a lot of what's going on your computers themselves is done in the stack methodology. That's why Windows takes freaking forever to start up. It's just like way too much crap on that. So stacks are just a memory address and memory structure. Just like your links are, they take up things. And you have to provide a link because it's not contiguous. So contiguous memory is indicative of arrays. So arrays have contiguous memory. It's going to block off all that blocks of memory that we need. Whereas linked lists and stacks and queues and all that, they're very indicative of how Microsoft saves files to the disk, whereas fragment, you can try to computer on a regular basis, right? Because there's no current anywhere. Well, they use this type of implementation with the linked list basically the same way to find all the pieces of your file. Your file typically is not contiguous memory space on your disk. It's going to be splattered all over the place because that's what Microsoft does. So we use stacks in the memory structure, and this is just one of the key ways that how computer programs actually execute their statements. And we really do put them on a stack. And so maybe you have acquisition records, different sequence of function calls, and whatever. It puts it in a stack. The last one in is the first one out. So now we talked about queues. Queues are very similar to stacks, except their implementation is first in, first out. So here is almost basically the same how that we did in the one. They integrate all of the queues with column 1 and column 2. Yeah. So how do these components are added to the end, but you have to actually use them from the beginning. So when we add a component to a queue, we actually And when we remove a node from the queue, we call that dequeuing. So an implementation example, a very applicable one, is air traffic control transport. So you can't have like 3 trains in a row and have the whole that fourth in line with get in front of everybody else and take off. There's no room on the runway. And air traffic control is one of the most stressful jobs in the world out there because they've got all these planes flying in all these directions and they're coming in and they're leaving and you don't want a mid-air collision. That would be pretty tragic. Make a pretty bad day for everybody. So air traffic controllers make sure that they get that shit organized so that we are in sequential order. So take airplanes taking off. I don't know about you guys, the controls is so great. Saving my time, but and we're going to see. It's so funny. Everybody comes here for spring break, and I was, there's nobody there. You should see one for crazy. All right. So, anyways, so airline, dreaming about my airplane flight to Colorado. Okay, so queues. Queues are again memory structure, and they really just store data in a waiting line. So new items get queued at the end, and we remove nodes or dequeue them from the beginning. And so they're different from a stack, whereas a queue is accessible from the beginning and the end, where the stack is only accessible from the last node that was pushed on. And so we follow with this when we're doing the first in, first out policy. So yes, you could just, in memory, you could just completely destroy the queue, but the correct implementation would be pop everything off of that queue before you actually destroy it. So our basic functions with queuing are add queue, and it just inserts attributes of the queue, and the EQ is the one from the front. Peak is a function where you can look at the data at the front most node, but you don't actually have to pop it off, and you don't have to EQ it. Other functions that we use typically with queues is checking to see if it's empty, checking to see if it's full, and then of course we can just clear the entire queue, but again, we're actually just EQing each node versus destroying the queue itself. So we came back around to recursion, and we went over this again. Yeah, we didn't actually talk about this in class. I picked up a set of slides that did not go in there. This is totally the next part of our recursion. So please disregard the data factorial and the factorial. They are not going to be examined. So then we start talking about base conversions, and I showed you how we convert from our most common bases that we deal with is binary, octal, decimal, and hex. So binary is basically how all your computers are going to function. There's basically considered a G number, and then your octal is base 8, and decimal is what we know as the base tiny number. There's really a deep. Another thing about the fact that we're counting in base 10 is just quite a lot. But the values go from 0 to 9. Remember, in computer science, everything starts at 0. So for base 10, our base number is 9. So I showed you, went all the way back to elementary math and started talking about how we do regular counting systems, and always to the right we have our ones, always to the left we have the thousands, and it just keeps going from there. And so if we wanted to actually rewrite this value, we could break it up into 2,000 plus 700 plus 3. And what that allows us to do from a base 10 perspective is now we can represent it from the power of 10. And so when we deal with the value of 2,000, it's really 1,000 times 2, and 1,000 can be represented as 10 to the first. And so then we get that 2,000. So if we continue with that process and continue breaking it down, our 700 is really 7 times 100, and that 100 is 10% of that. It is. It's completely based on place value. And here the next thing is that 1 of 10 value, so that's really 1 times 10 to the So what that does is each one of these digits is really equivalent of a bit. And each place is that certain power that it takes. So what happens is, if you look at this, it doesn't matter. It doesn't matter what our base is. We're always going to start with one. We're always going to start with whatever that base is, raised to the 0 power. And put down 1. And then the next one is to 10. And then the next one is to 100. So your next one is to 1,000. It doesn't matter what this number is. Just knowing the placement of each one of those values. So we can take this same methodology of the base 10. We can actually use the whole base 5. Is that a valid base system? I don't know. Not everything that I do is going to be not. So as long as you understand, it doesn't matter. So at base 5, that means our value is 0, 4. Again, if we start all the way to the right, our 4 is going to be 4 times 5 times the power, and that gives us 4. And then the next one is going to be 1 times 5 times the power. And then the next one is going to be 3 times 5 times the power. And we add all that up, we can get a calculation. So it ends up being base 5. So we really just convert it from base 5 to base 10. You can do any base to base 10. It all functions the same way. You always start at the rightmost value, and it's going to be the raised to the power of 0. And 1, 2, 3, and it just increases by 1. So that's what the conversion up here is. What you're seeing is this representation. And so here we're using some arbitrary base 9. I told you I worked on a computer system that was Unisys proprietary 9-bit system. So that actually exists. And so the only way I could debug my code was to dump all my data to octal and then convert it manually to ASCII. So yeah, you really do care about this. It's something that you might run into someday and have to be able to use. So here, I think it was in the 11th reading class. I asked you guys, how many of you are familiar with Wireshark? Have you used Wireshark for networking? Alright, so let's check this out. So this is just an example of a very current application that I use on a regular data set when I was working in the industry. So Wireshark is a free networking tool that will package into dual copy networks. And why do we care? Well, one of the things I had to do was I had to create packets bit by bit, and I had to send them to another computer, and they had to translate it back out. And so the data started out in ASCII format, and I had to convert it to bit format, and then I had to transmit it over the network in a way that it ended up in the right format on the other end. So how I even know what was going on is using Wireshark. So here I'm going to use my wireless. I'm going to start sniffing the packet. So here you can actually see all the transmissions that are going on right now. So if I go to here and go to Google, and you'll maybe see something like there we go. So you can see that now the IP addresses, everything changed. You see that as that data was going across the network, look at all the IP addresses. So this is my source. This is my IP address that I've been allocated here, connected to UCS network. And then here you can see where I'm querying different places, where I'm going to different IP addresses to get the go to Google. And so here you see that we get an ACK back, ACK is knowledge. And so we're like, yeah, okay, I got that page in back. And then if I Google something, colors, Illinois, you can see that the data that came back. And then if I actually, you can see here where a Cisco router is trying to figure out who this IP address is. And then finally I can go to some other website and you see as that data is loading, you can watch the network traffic happen. So what is this right down here? Look at this data right here. What is this? What base is that data in? Hex. The data is in hex. So it's usually not that helpful if you can read it, right? It does try to translate it. It makes an attempt to translate it here in ASCII, But some of the traffic is going back and forth. It doesn't translate. It's just computer speak network that we're talking about to each other and stuff. But you can see all the different hex values. So it is useful to know the different bases because they're used all the time in your computers, even if you're not aware of it. So you can just sit here. This is how they find hackers and stuff like that. Is they use network sniffing tools like this. So we can convert from any base to any base. So what happened was Wireshark, what it was doing was it was getting to explain the data at. No, I'm not very favor at all. I didn't realize it was sorry. So you can translate from any value to any value. And so what happens is what Wireshark is trying to do when it's sniffing a packet and it's representing the data in hex, it is trying to translate it to ASCII. You look at the hex value, and then you convert it to base 10, and you look at your ASCII character chart, you see that they actually translate. So it doesn't really matter what your base is. So, like, for example, here, this is binary. And this is one of those binaries how the computer system functions. So, base 2. So that means that the possible values are 0 and 1. And here I just have a quick chart that shows you the conversions up to 16. So when you're doing a typical binary, it carries 4 characters to represent them. Unless you're dealing with octal, octal going 3. Because we only need 3 to represent octal, but the highest number in octal is 7. We don't need that 4th bit. It's not doing anything for us, okay? So here, this is just a quick demonstration of binary. So hex, I was just showing you some examples of hex. That is right, we also use it a lot with doing HTML columns to represent the rest of the fluid and how we can use our cells. So here with hex, that's basic 16. And so with 16 though, or wait, we only have numbers 0 to 9. So how do we get the next 5, right? 4, 5, 6, 7, 8. Okay, so that's the code. So we actually go off the code down to add the foxtrot. Now, uppercase, lowercase are both fully valid, but if you're writing a program to deal with it, you're going to have to take a case. Because, or you have to be able to translate back and forth in exact lower and upper. So this is just, these are your hex values. So the alpha is actually 10, alpha is 11, up to foxtrot is 15. So again, hex is something we use. It's out there. We're using it all the time. Then we have our octal. Oh, that's our hex. That's our hex representation. So if you're actually representing this data, so you go from hex to decimal, again, you just keep the placement of it. So we have our 2 values there. We have our alpha, and then we have our 3, and we have a delta. So that is our distribution 0, 3 distribution 1, and our alpha position 2. So just like any other base, we convert it the same way to get our decimal value. Now, one of the interesting things, though, is because 2 of our bases are the perfect power of 2, we can also use binary to do the conversions on it because it makes it just as easy. So here, because it's base 2, we can just go ahead and translate those. Because again, a foxtrot here, base 10, is the same thing as 1111 in binary, because all 4 bits are set. It's the same thing as the foxtrot in hex. And so you can automatically make those conversions back and forth. And so here's an example of it. So we have a hex 0, then a 10 is all 0, and you see when we get all of those here, we have a foxtrot, which is 16, and we get a 1111 and all of them set. So here's the translation. So instead of 10 in decimal, we're doing a 10 in binary, because position 8 and position 2 are set. You add these 2 together, we get 10, so that's your alpha. Then we have a 3, so to get a 3, we have to set bit 1 and bit 2, add them together to get that 3. And then we just calculate not going to change the value of it. And then the last one is your delta. So your delta is the value of okay, so on 13, delta is 13 in decimals. You represent that in binary by saying you get 8, get 4, get 1. So you add them together, you get 13. So you can do that with any value explicitly. It just says that it's on the exact same way. Yes. Okay. So this is just showing you, as long as we follow that same equation, so if you want to reverse that, go the other way. So we're going to do decimal to binary. So decimal to binary, you want to represent the values for the center. Now I showed you my old school implementation where I just started writing out from 1 up to 0 whatever that my values, and I just do my block support. But there is an easier way to do it is to use division. So to choose a division on this guy right here. So we have our decimal divided by 2. And this same implementation works when we got the opposite decimal hex and yes, that's it. Okay, so here you can modify that base. So you take the decimal value, find the base, and whatever that remainder is, that's what's going to actually represent your conversion. So you just keep dividing to get to the point you have a value of 0, and then you have the remainder, and you can look at that and go, okay, so decimal 27 is equal to just binary 11011, and we can prove it by looking at the bits and their values, because we have the value of 1 is set, 2 is set, so now we've got 3. And then 4 is not, but 8 is, so the 8 and the 3 is 11 plus 16, so 16 is set, and that gives us 27. So we can do the math and that's pretty quick, but you know, if you have a really large value, 25 is pretty simple, but if you have a really large value, you don't convert to either. This next value right here would actually be easier. And this you can actually code. My implementation you can't code. So again, just a larger number, same thing. This one is not a palindrome like the last one, so it's a little bit easier to see how the data lays out. So what happens here is the values at the bottom start to on the leftmost side instead of to the right. So conversion decimal is another base. So the last example we looked at was a base 2. You can do base 16, you can do a hex. You can have any other set of base. Here's not a valid base that is out there, it's not been. So you can still convert, it totally works. Now, when you're dealing with any base to any other base, so you're not involved, it's not a base 10 to something, it's not any of the ones that we've looked at so far. So, depending on what the bases are, there's a basic two-step process here. So we take that base and we convert it to decimal, and then we can take that decimal and convert it to the next base. So converting to decimal really is just a stepping stone. So the example here is a really good example, because we want to convert from 7 to 4. So there's no commonality between the 7 and 4. So we really do need to convert from base from base 7 to base 4. So we do have base 7 to base 10. We do our calculation here. We go from 7 to decimal. And then from 7 to from decimal, we can convert to anything. So from decimal, we can start doing the division. So here now we can divide that decimal value by 4, and then we can get what our value is here. And then we have our base 7 to base 4. So it really is just a generic conversion process here. So one of the great things is you're dealing with any of the bases that are a power of 2. So your binary, your octal, and your hex are all powers of 2. So you can actually convert, instead of the base 10, you would actually use base 2. Because they have that all in common. And so So one of the most common things is converting between basic and basic. And so here what we do is the first thing we do is take our basic down and we create our tax representation of it, and don't forget that has to be block 4. But then when we go to octal, it really is in blocks of 3, right? So we would separate our data instead of the blocks of 4. We would actually move in blocks of 3 because the highest value in octal is 7. So if this bit is set at 1, this bit is set at 2, this bit is set at 4, that gives you 7. The highest value can represent an octal. So if we convert that here, you see that we're going to group them in sets of 3 from right to left. So if we do that, this is what it looks like now. Instead of a block of 4, we have a block of 3. And then we convert that to octal, and that's how we can convert hex to octal. So we just, binaries are stepping stone. Aren't you excited? Okay, I still have 12 minutes that I owe you. Questions, concerns, alibis? Yeah, before you Scantron on Wednesday. We'll have Scantron or UCID. I'm sorry.